Hi students, this is the instantaneous rate of change problem from the exit ticket. It's an application problem about a melting ice cube. So the situation was that the ice cube has a side length of 9 centimeters, and then we were given the volume of the ice cube as this 9 minus 0.5 t, where t is time in minutes, that quantity cubed. Volume, of course, we have length times width times height, is going to be measured in cubic centimeters. So the question wants you to find the instantaneous rate of change at 2 minutes. Okay. So let's first find the, at 2 minutes, what the volume is going to be. So let's look at V of 2, and we have 9 minus 0.5 t cubed. Oh man, I gotta put that t value in there. Oops. Okay, and that's cubed. So when I plug that in, I get 512. So V of 2 is 512. That would be the volume in cubic centimeters. Okay, centimeters cubed. All right, so what we're looking for, we do see that we have a cubic, okay, and we can talk a little bit about, the standard cubic function and then what's happening with this. But let's see what we can find out here with this at 2 minutes, what's going to be happening. All right, so let's see. Let's go ahead and start drawing in our table. Let me get rid of this for now. And we have the average rate of change between 2, 512 and a close point. We're going to put that 2 minutes right in the middle here. And let's see. So we have 2.1, 2.01, 2.001, and 1.999, 1.99, and 1.9. So we need to come up with our formula. So again, that's the change in the outputs divided by the change in the inputs. So V of t minus V of 2, that's the one point we actually do know to be able to plug in right now, and t minus 2. So V of t is this formula, 9 minus 0.5 t, all that cubed, minus 512, because it's the output, take away the output, and then we'll have t take away 2. So this is, again, what you would be plugging into your calculator. Whether you use a table feature or not, you must have parentheses around the numerator and around the denominator. So from here, I'm going to tell you what I get in my table. I get negative values, 95.4, negative 95.94, negative 95.99. So sorry, excuse me. Awesome. All right, negative 96.01. Let's see if I can hold these coughs in. Okay, so hopefully we can see, again, we're converging towards this negative 96. If you're doing these and you're not approaching the same value, something is wrong. And likely, in my opinion, it's going to be these parentheses, or that your original setup for the formula is incorrect. So make sure, if it's not converging to the same value, that's your sanity check to say you need to look for where the mistake is. Okay, so from here, so we can say that the instantaneous rate of change at 2 minutes is negative 96. And it's negative 96 cubic centimeters per minute. Remember, when you're finding this instantaneous rate of change, that's a slope. It's a slope with a tangent line, so it's a rate of change. So you need to have something per something. Now, when it asked you to interpret, I saw a lot of answers that were kind of like this sentence here, but not really explaining the context of the ice cube. So we want to say something like this: at exactly 2 minutes, the cube is melting at a rate of 96 centimeters cubed per minute. The negative value is due to the fact that the volume is decreasing. So when it's an application problem, you need to step further than just the solution or just the answer that you've calculated and explain, well, what does that mean in terms of this problem? And that's what we really want to look at. What does that mean? And that was the same with the velocity of the ball. We did a problem, one of the first ones in this lesson, 6.10, that was talking about the instantaneous rate of change for this ball at a certain time. That was the same type of situation. We get to the answer, but we have to explain, what does that mean in terms of the path of that ball? Why is the rate of change positive or negative? What are the labels? So we want to really make sure we have that rate written down as well.